Hello, Honors Chem students. Mr. Keister here with you again today. This is the video for Wednesday, September 9th, 2020, which is, hello, I'm back, our 14th day of school, our scheduled 14th day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the order of the lessons will remain the same regardless. Let us look at our do-nows, our schedule for today. So today you are going to look at page 24, lab activity 1-2 part B. We're in our discussion of density. Yesterday we graphed some data, mass versus volume data for both copper and zinc, which was lab activity 1-2 part A. We established a relationship of the ratio of mass to volume, which is equal to density, is also equal to the slope of a line that graphs mass versus volume. And we're going to start today by going over the rest of those questions that were assigned to you as homework. And then we will go on to part B. I'll cover around half of part B in class, and you are to finish the rest of it as homework, all right? For tomorrow. And then also a reminder that your next online homework assignment in mastering is due this coming Friday by 7:30 a.m. That is 1-1B measurement. Okay, due this Friday by 7:30 a.m. So let's look at lab activity 1-2 part A and finish that up first. Okay, so here's from yesterday. Of course, I don't have the stuff back on there that we wrote yesterday. I did keep over here on the board, though, the graphs that we talked about and the relationship between mass, volume, and density. So I left that there so we could refer to it if we need to. And I think we were ready to do number 8. So let me advance the screen and start with that. So we established in number 7 that copper was more dense than zinc based on our graph here, seeing that copper had a greater slope. And so copper is more dense than zinc. And so in question 8, you were asked, in the boxes below, draw a particle diagram comparing a piece of metal A, copper, and a piece of metal B, zinc, assuming the pieces have the same volume. Okay, so copper and zinc are both monatomic elements. So we can represent them with singular particles, okay? And so remember, copper has a density of 8.60 grams per ml or grams per centimeter cube. And this was zinc, where the density was 6.50 grams per ml or centimeter cube. This said that these were the same volume. So I'm just going to pull, this is grams per ml, meaning per 1 ml. So let's just assume, for the sake of argument, that each of these boxes represents 1 ml. Well, based on that, copper would have 8.60 grams per that 1 ml, so approximately 9. So a reasonable representation of that would be to put 9 particles in the box. Right? Since I can't put 8.60 particles, we'll round it to a whole number. So let's see. I'll just use X's for copper. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Something like that. Okay. And then let's look at, let's do that a little bit. So zinc is around 7, give or take, 6.50. And so let's draw 7 within that same space. So I'll use circles for zinc. So let's see. 1, 2, 3, 4, 5. Okay. So let's think about this, all right, and how these drawings are compared to each other. So one thing I would ask you to know is that density effects the number of particles, all right, in a given volume. All right. Remember, the quantity of matter is mass, all right, and grams is a measure of mass. And so what the bottom line is, if you have more particles in the same space in copper than you do particles of zinc in the same space, then those spacing is going to be different, all right? And thus the spacing between the particles is different. I tried to illustrate that here. I don't know how good I did or how well I did, but hopefully you can see that with more particles in the same space, that they're going to be closer together, all right? So things that are more dense than others have closer spacing than the other thing that has a smaller density, all right? Basically, density is a measure of how many particles you got jammed into a given space, okay? And the more the particles there are in that given space, the more dense it is, okay? All right, so let's look at the back side. Number 9, we have talked about this before actually in our notes. Been maybe several days or a week or so. Asks us to write the definitions of precision and accuracy. They are different. Yes, indeed they are. So remember, precision, I'll just kind of paraphrase this. Precision is how close you get, your measurement is, how close you get to the average of everyone. All right? How close your measurement is to the average of all the measurements that were made in the same way. And accuracy is how close you get to what you're supposed to get. In other words, how close is your measurement to what the measurement truly is, okay, based on the standard. Okay? So then question 10 asks, how precise is your class data? And explain how you know. Okay, so let's look at the graph, all right? So all these individual points here, let me scoot this over for just a second, get a little closer. There we go. All these little points here represent each individual piece of data, all right? And the best fit line is what? Is it not the average of all that data? Yes, it is, all right? And so a measure of precision, which is how close you got to the average of everyone, well, if the average of everyone is the best fit line, a measure of precision is how close these individual dots are to the line. And honestly, on the copper line, almost all the dots made the line, and if they didn't, they're very close, all right? And the same, just by happenstance, the same is pretty much true for the copper data, or the zinc data, I'm sorry. So based on that, I would say, I'll put this back. Based on that, I would say that they're reasonably precise, if not really precise. And how you know is all the data points were either on or very close to the line, our best fit line. So that there really weren't any major outliers where you had dots way far away from the line. So that's good. No major outliers. You will get outliers, okay? But again, you have to take those with a grain of salt. That's why they're called outliers. They, for whatever reason, measuring was done incorrectly, or the interpretation was incorrect, or whatever. It happens, okay? How accurate was your data? If the actual densities are 8.96 grams per ml for copper and 7.13 grams per ml for zinc. Well, just to recall, our class got 8.60 grams per ml for copper and 6.50 grams per ml for zinc. Remember, accuracy is a measure of how close you get to what you're supposed to get. So these numbers here that are stated are the ones that we were supposed to get, and then I wrote in below what we actually got. And I would say that both class densities were fairly close. To the accepted value. Remember, we call accepted values, we also call that the theoretical values. The accepted values of both densities. So here again, not only was the data precise in that it was very close to each other, but the data was also accurate in being close to what the true values actually are. Okay, so this worked out pretty well. The data was both precise and accurate, so that's good. All right, that takes care of part 8. Hope everybody understands what we were trying to accomplish here. Okay. All right, so let's move on to part B. And I think now that I can remove all this, and I think we're done with this too. Probably refer back to things we learned from it, for sure, but I don't think we need that on the board. So in part B, we're going to look at some more density problem-solving type scenarios. So number 1 asks us to study the matter shown in figure 1. Each dot represents a particle of matter. Assume the particles are uniformly distributed throughout each object. Particles of the same size have the same mass. Based on that, right away, I would say that we are looking at 2 samples of the same substance based on the appearance of those particles and the spacing between them. I'm just saying, that's what I would say. But we'll see here. So in the table below, show how the masses, volumes, and densities of A and B compare by adding a symbol greater than, less than, or equal in the second column. So mass. So mass is determined by quantity of matter, which was represented by number of particles. And if we want to know, so how do the masses of A and B compare? Well, if you look, there's a heck of a lot more particles in this box sample than there are in this one, which means the mass is certainly greater in B than it is in A. So the mass of A would be less than the mass of B. And again, less particles in A means less mass, because that's how we represent mass, quantity, number of particles. Okay? Volume. Okay, well, volume is represented by the amount of space the particles take up. In this case, in the diagram, basically the size of the box. All right? So again, A's box or sample is quite a bit less than B's. So there's less space taken up, which then would translate to less volume. Okay? Now density. So density is a ratio of mass to volume. We said that basically translates in a particle diagram to spacing. And again, based on the fact that these particles not only look identical, which is kind of a dead giveaway, but the spacing between them also appears to be the same, I would say that the densities of these two are equal, and that we're basically looking at two different samples of the same substance. For example, this could be a smaller sample of copper, and this could be a larger sample of copper, kind of like we had back in the lab with part A. So that would be my guess anyway. So the size and spacing of particles is the same. And thus, so is the density. Okay? All right, let me advance the screen. In figure 4 below, a graph shows the relationship between mass and volume for two substances, A and B. So here we're looking at mass versus volume. So remember the line, mass versus volume, the ratio of M over B is density. So basically what we're saying here is that the slope of A equals the density of A, and the slope of B equals the density of B. Okay? All right, so there we go. Now, part A, you have built a simple two-pan balance. Boy, this is like the old days, all right? This is way before electronic balances. Shown above to compare the masses of A and B. What would happen to the balance if you put equal masses of A and B in the two pans? Well, for instance, if you put 10 grams of A in the A side and 10 grams of B on the B side, equal masses, all right? So what would happen? Well, what does a balance measure? It measures mass. If the masses are the same on either side, then the balance is going to remain level, all right? What about if you put equal volumes of A and B in the two pans? Well, let's look at that. So let's just pick a volume. I actually picked 40 mLs, all right? So if I have 40 mLs of A and 40 mLs of B, all right? So let's look at that. So here's 40. Here's the mass of 40 mLs of A. And there's the mass of 40 mLs of B. Well, looks to me like it's a little above 50. Again, these are to the ones place, so I'll say to the ones place. So I'm going to say it's somewhere around 52 grams. I can't really say with certainty. It's subjective. And B looks pretty much like it's right on 20. So again, around 20 grams of B. So take a look at that. Same volume. Here's the difference now. Well, this is what density is right here. Same volume of A and B. You got 52 grams of A over here and 20 grams of B over here. What's the balance going to do? Well, A has more mass, so it's going to tilt towards the A side. All right? So A has more mass. So balance tilts towards A. In other words, this side over here, down she goes. All right? Next, part B. Find the slope of the line for both A and B. Slope. Okay, so slope is rise over run, change in y over change in x, y2 minus y1 over x2 minus x1. So basically, how many points on the line do we need to calculate slope? And I think you already know the answer to that is 2. All right. Now let me bring up an important point. what point is always valid on a mass versus volume graph? And if we talked about this yesterday, and if you said 0, 0, you are correct. All right. So always 0, 0 is a valid point on a mass versus volume graph. So if 0, 0 is a valid point, why not use it as one of your points when you're finding slope? Think about it. You know, y2 minus y1, you can pick any two points on this line, and you have to analyze, you know, what they both are and then subtract one from the other. But if one of the points is 0, 0, then you don't have to subtract anything. So basically, the slope of a line, if you're able to use 0, 0, can simplify from the change in y over the change in x to simply y over x. So, you know, why not? Again, just trying to make it a little easier. So let's do A. So the slope then is y2 minus y1 over x2 minus x1, but we'll just use 0 as our 0, 0 as our first point, all right? And so basically we're just y2 over x2. So let's find a point on the graph for A. Well, this one here is pretty easy to tell. I'm just going to grab this point right here because it's obviously on 80 and 60. So y would be 80 minus 0 technically, or just 80 over 60. And so the density then, or the slope of the line, would be 80 divided by 60. Now, I realize that these are all zeros. However, given the fact that they list the 0 here, I'm going to assume that technically they should have put a decimal point after each of those, that it's an exact number, okay, that it is indeed 80, and so that 0 becomes significant. So based on that, I'm going to assume that we're going to round it to 2 sig figs. So this would be 1.3 to 2 sig figs grams per ml, which also is the density. I'll put that there. Equals the density of A. Remember, the slope of a mass versus volume graph is equal to density. Now for B, we have slope equals y2 minus y1 over x2 minus x1. Here again, why not use 0, 0 as our point number 1? And let's see. Here's another, let's just use this point right here, because here again, it's right on the intersection of 40 and 80. So this would be 40, technically minus 0, over 80 minus 0, which would be 0.50 to 2 sig, which then would be the density, excuse me, of B. So you can see the density of A is, excuse me, 1.3 grams per ml. Density of B is 0.50 grams per ml. A is more dense, and as you can see by the slopes of the two lines, that bears that out. Okay. Letter C, if you put 10.0 mLs of A in one balance pan, how much mass of B? Okay, this is a volume. What mass of B would you need in the other pan to make it balance? All right, well, let's look at that. So 10.0 mLs of A, which would be right here. All right. If I go up to the A line, right there, and come across, it appears to me to be around 13 or 14 grams. I'll say 13. 13 grams of A. And if you want the pan to balance, then we need the same mass of B. All right. So need 13 grams of B to balance. Remember, the balance measures mass, so the masses have to be the sink. If you put 35.0 mLs of B in one balance pan, what volume of A would you need? Okay, well, now I'm getting tricky now. All right, so let's see what mass. Remember that the balance doesn't balance volumes. All right, it balances mass. It balances masses. So let's convert these to masses. So 35.0 mLs of B. What is that approximately equal? Okay, well here's 30. Here's 35 right here. If I go up to the B line and come across, looks like it's a little more than 15, maybe 16 or 17 grams, somewhere in there. Again, I'm just trying to guess as best I can. I'm going to say 17 grams of B, all right? So we're going to need 17 grams of A to balance, okay? The masses have to be equal. Well, now we have to translate that 17 grams of A to volume. So I want to know what volume of A we need. So here's that 17 grams right here. And if I come across to the A line, which is right there, and come down, now we're right there. And it looks like, well, there's 10. There's 20, so halfway would be 50. Looks like I'm a little bit shy of halfway between 15 and 20 mLs. So I'm going to say it's about 14 mLs of A to balance. So now let's think about that. A is more dense than B. It's going to take only 14 mLs of A to balance 35 mLs of B because A is so much more dense. Remember, the balance measures equal masses. And in a given volume of A, you're going to have more mass, all right? So you're going to need less volume of it to balance a certain volume of B. That's a really good question. And it brings home how important it is to be able to read a mass versus volume graph and interpret it. And then letter E. A liquid has a density of 1.00 grams per ml. That ring a bell with anybody? 1.00 grams per ml. Anybody know what liquid that might be the density of? I'll bet you know. It happens to be water. Definitely. All right. Sketch the line representing this liquid on the graph in figure 4. Okay, so, well, what can we use for one of the points? How about 0, 0? Okay. And then if the density is 1.00, if it's 1, then that means mass over volume equals 1, which means mass and volume must be equal in value. So we can pick any point on here where that's true. So for instance, I could use 60 and 60, or 50 and 50, or 80 and 80, whatever. I'll use 60 and 60. So here's 60, here's 60, and right there is where they meet. All right? And so now I have 2 points, 60, 60, and 0, 0. I can now draw my line. That's all we need is 2 points. Now, I don't have a straight edge with me here, so let's see how badly I can botch this up. Well, that's not too terrible. I'll make my dot bigger. There we go. Now it's fixed. So this then would be the density of water, 1.00 grams per ml. Okay. Remember, we established that B was 0.50 grams per ml and that A was 1.3 grams per ml. And as you can see, this water falls in between those. Okay? So, which substances will sink when placed in a bucket of this liquid, in a bucket of water? So you put A in water, it's more dense than water. What's it going to do? Sink. All right? So since I'll write it down here, hopefully you can see it. Since the density of A is greater than the density of water, it sinks. On the other hand, the density of B is 0.50. It's less than the density of water. What happens when you put that in water? Floats. So the density of B is less than the density of water, which means it floats. Okay? Floats. Good exercise there. That's a good one. Let's go to the back side. This is some really good stuff here. This graphing and interpreting graphs. Good stuff. Refer to the table of densities at the right to answer the following questions in number 3. All right. So over here we look at some densities. All right. And it asks us to take a look at it. So let me explain something here. And I think we've already mentioned this before. So, and it asks us here, we're going to sketch a mass versus volume graph for titanium, copper, and mercury. So we got titanium, copper, mercury. All right, those 3. All right, so let's just use titanium's listed first. Let's use this as an example. So example. For titanium, D equals 4.54 grams per ml. All right? What does that mean? That means that there's 4.54 grams per how many mLs? Think about that. When you're going a speed of 60 miles per hour, you go 60 miles in 1 hour. All right? If the density is 4.54 grams per ml, that means there are 4.5 grams per 1 ml. We don't put the 1 there, but we call this a complex unit, a ratio of 2 units. There is a number associated with that unit, the denominator, and that number is 1. All right? 1. So, how does that help us here with plotting a graph? So the density can actually be plotted. All right, we can use that as a density point at B equals 1 ml. What's another point we can use? 0, 0. So if we only need 2 points to make a line, right? So if we use 0, 0 as 1 point, and the density of the substance as 0.2, which would be its mass graphed at 1 ml, we got our 2 points, away we go. All right? So let's do that for these 3. So titanium is 4.54. Well, here's 1, 2, 3, 4, 6, 7, 8, 9, 11, 12. All right? So 4.54 is about halfway there, and that's at, I'm sorry, we're going up here, my bad. This is volume. All right, so the volume's 1 ml right here. The density is 4.54. Well, here's, let's see, 40, 30, 20, 10. So be about halfway between 0 and 10, and then it's at 1 ml. There's my second point right there. Again, I don't have a straight edge, but there you go. There's the density of titanium. Copper, 8.96 grams per ml. So at 1 ml, we have close to 10 grams. There you go. There's the density of copper. And then mercury, 13.55. So again, at 1 ml, now we're up to, well, between 10 and 20, not quite halfway. And so there you go. There's the density of mercury right there. Okay? So we only need 2 points. 0, 0 is 1. The density of the other, because the density is how many grams there are in 1 ml. So you can use 1 ml as your volume and find the appropriate mass. You got your 2 points, draw a straight line, boom, you got it. All right? Part B, you made some cubes out of each metal in the table that each measure 2.00 centimeters on a side, all except mercury. Why can't you make a cube of mercury? Well, mercury is a unique metal whose melting point is lower than most temperatures we experience normally here on the planet. And so because of that, mercury, is, even though it's a metal, is a liquid at most temperatures, especially room temperature. And so it's one of very few elements that is a liquid at room temperature. The other one, you know it by chance? It happens to be bromine. Right? So bromine, and which is a diatomic element, Br2. So mercury and bromine are both liquids, normally. All right? What is the volume of each cube in centimeters cubed? Well, remember, a volume of a cube is, well, it's length, width, and height, or since in a cube, those are all the same, so you could say side cube, either way. So volume is length, width, height, or side cube, 2.00 cubed, or 2.00 times 2.00 times 2.00, equals, well, 2 cubed is 2 times 2 times 2, 8, but it's not 8, because that's got 3 sig figs. Don't forget that, and we're multiplying. So it would be 8.00 centimeters cubed, or you could say 8.00 mLs. Remember again that an ml and a centimeter cubed are equal. And again, we're at 3 sig figs, so don't forget that. So we showed our work, we're good there. Given the volume in B above, find the mass of these metal cubes. Lead, nickel, and zinc. I'm going to do one with you, and then I'm going to assign the rest as homework. So let's do lead. So we need to draw a density line for lead. So here's lead right here, 11.35 grams per ml. Lead's pretty dense. So again, lead at 1 ml is just slightly above 10 at 11.35 grams. So using 0, 0 as my other point, and there we go. So there's the density of lead right there. So given the volume above, find the mass of these cubes. Okay, well, I'm going to show you 2 ways to do it. We can do it graphically. Just analyze the graph, all right? So at 8 mLs, which is right here, we can go up and find the mass graphically. So if I go up here to the lead, it's about right there. Almost, so here was 8 mLs, and there we are. And it looks like it's very close to 90, all right? Very close to 90. So maybe slightly less. It's almost. So let's say from the graph, it appears to be around 89 or 90 grams. All right, we'll say 89. It was just barely not quite at the 90. And again, I used to go into the whole number here because all these are to the whole number. So that's what we did there. All right, now you can also do this mathematically. All right, we've already established the mathematical relationship between mass, volume, and density. All right, and it's to go right here, but I'm going to write it over here just so you can see it better. So remember, density is mass over volume. So I'm going to write that over here so we can see it a little bit. So D equals M over V. All right? Well, we have the density of lead, which is 11.35. We have the volume, which is 8.00 mLs, right? We do not have the mass. Okay? So there you go. We're going to solve for M. All right? Well, if I just, slap a 1 under there and we could cross multiply, because all we got here is a proportional ratio here, we can just cross multiply the two and get the answer. So M times 1, or just M, is equal 11.35 times 8.00. And based on the multiplication and the fewest number of sig figs, which is 3, now we get 90.8 grams. 90.8, 3 sig figs. So if you do it mathematically, again, this work should have been down here. I'll just go ahead and write the answer there. I get 90.8 grams. You notice that doing it mathematically gives you a more precise answer, which makes sense because isn't reading a graph got quite a bit of subjectivity related to it? It's not going to be as accurate, all right, or as precise, either one, really. And so the slight difference there in the numbers, but honestly, you could do it either way. You could do it either way. So I'm going to leave nickel and zinc for you to do, and then problem 4 is very, very similar to what we did right here with problem 3, and I'll have you do that on your own as homework for tomorrow. I think you're going to find a very interesting result once you finish number 4. So that's it for today. So finish this up as your homework for tomorrow, and until next time, stay safe and stay busy. Keep working, and I'll catch you next time.